Hello? Okay. Yeah, I said I would stream 2 hours ago, but here we are. Some stuff popped up, but I got hot chocolate, and it's past midnight, so I'm gonna see how long I can go. Alright. Let's find out. Let me clear up all these tabs. It's too much. Oh, I closed Twitch. Alright, let's see. Next programming. Hi, welcome. I'm gonna stream. I'm gonna start the stream proper in a little bit. Okay, it's been more than 1 minute. Okay. So. Alright. There's some things I need to do. So, let's go over what I did last time. We can start with the git log. Stream with 4 teams. We did basic implementation of improved colored topological sort. Okay. And then struct definitions and type symbols. So, all we did was sorting. Essentially just sorting and structs. Now let me explain that sorting for you. So I had a bit of an issue last time when I was doing the sorting, and I rewatched the clip. And I think I put a description. I put a comment in the description of the VOD on YouTube. Essentially, sorting works now, and I can show you one of the best things about that is specifically this mutually recursive functions. So let's just start by doing this m, and then we'll repeat that a couple times. I put this example inside my announcements. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is m0 to m9 right here. m0 to m9. Okay, and we're going to turn these into functions. So let's just go multi-cursor, put the function right here, and we'll add another line at the below, and then we'll highlight these. We'll go here to the ends, and click go 1 line down, equals, paste, and then just put that at the top. Alright, now we've made basically a ladder. We've made a ladder of mutually recursive functions that go from this, down, 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 all the way to m9. You're calling I'm supposed to call m. Where's m0? Does m0 ever get called? Oh yeah, m9 is where it starts. Okay, so now when you look at this, right? How do you compute its what is it? How do you compute its return value, right? How do you compute its return value? You can't. So you do a function like this, and you can do a colon something, right? A colon this. This is essentially your this thing right here. This is your type annotation, the return type annotation. So these functions have no return type annotation. So if you were to go and try and calculate the return type, this would not only put the compiled program in an infinite loop, it would put the compiler in an infinite loop. So you don't want to allow this. So let's see what happens when you run it. Right? Let's see what happens when you run it. Let's put this at the side. Let's go full screen. Enter. And then we'll zoom out a little bit. Make it clear. All right. So let's put this in. So parsing file a.rec. It's called a rec because I haven't figured out a name for the extension. All right, haven't even figured out a name for the language. So it goes main.m9, m0, m1, 2, 3, 4, 5, 6, 7, 8, all the way here, and calling the next bit of the function. So what happens? It raises an error, as it should. Mutually recursive function m9 needs return type annotation. So let's control click here, and m9. So M9 needs return type annotation because you're checking M0, and the program has determined, and I'll show you where this gets this error gets raised. It gets raised in here, in check reorder. So before I explain that, I'm gonna here. So this is the reorder pass. The reorder pass orders symbols topologically so that further passes can iterate over symbols dependency free. So when I get to a function, let's say I'm type checking function A and it calls function B, when I'm in the process of type checking function A, it's already done function B. So this is a topological order. Everything is dependency free. You go top to bottom linearly. And that's what I was doing last stream. So I basically stabilized it right now. So yeah, right here, this is a requirement for type checking in most other passes. So currently, symbols are three different things: functions, globals, and user-defined types. These are type symbols. So here, note type symbols are self-referential types, also unique, bound to a name, and they don't make sense to be interned. Basically, just internal implementation detail. So the reorder pass is a lot more than just reorder. It also identifies cycles and self-dependencies. It also checks that all symbols are valid. So these are the sanity checks. Does this symbol exist? So it checks if like it's resolved. Is this type cyclic without indirection? This is an infinitely sized type. And 3, is this global / cyclic self-dependent? Oh yeah, is this global cyclic / self-dependent without an indirection? So this means, let's say you have a global A equals A. That's an error. Or global A equals address of A without a type decal. What is it called? A type specifier. So those are the two contexts. And 4, is this function self-recursive without a return type annotation or mutually recursive? This is our example right here. They're mutually recursive. And 5, is this symbol used in the right context? So it has to be a type symbol in a type, function or global in a function, or yeah, basically, yeah. So I basically run over these things, rsym PO for post order. We can keep it in post order, no need to reverse, because our post order is our topological sort. And this is what we were doing last stream. All of it done last stream. So this error right here, mutually recursive function M9 needs return type annotation. So it goes right here. It says here. So this is in user definite successor. If successor sort color equals sim sort gray, so this means it is a cycle. And switch successor.kind. And if it's a proc, it goes successor. If the return type is type infer, which means there is no return type annotation, this means it's an error. So this also means if you have main equals main, calling it, right? I mean, you can't do that. There's no return type annotation. It's just an infinite loop. So anyway, you get in here. There's no return type annotation. There's going to be an error. So if the successor equals the current symbol, this is a self-recursive function. So self-recursive function needs return type annotation, but if they don't equal, it cycles self by any amount of nodes and then back to self. So raise an error with pause. Mutually recursive function %s needs return type annotation, and that's the error right here. So they have two different symbols and they mutually recurse, and you're going to raise an error because there is no return type annotation. So let's just follow what the compiler tells us. So let's put this on the side and we'll go right click, enter here, M9. So let's go to M9 and add a return type annotation. Let's just make it that. All right, we'll just make it empty tuple. It's empty, nothing. And let's run it. Okay, perfect. So I'll tell you what the text means. This is good enough. Okay, I'll tell you what the text means. So parsing file, and then here. This is what you saw before. M9 all the way down, and that's the return type annotation. So it just runs. Check main.0, M1, M2, M3, M4, M5, M6, M7, M9, M8, and M9. And it gets all these types. And then this is what happens at the end of the type checking pass. So it has M9 equals that, and these are all having the correct return type annotation. But you can see there's a difference here. You see there's main.m9 is not being called, right? I'm not calling the function here. But when you get to here, it's called, right? It's got a call expression. Now, I'm going to explain why these are calling. I'll explain why, because I'm taking something from UFCS, Unified, what's it called? I think I wrote about it. Unified Function Call Syntax. Yeah, so I'll explain. So if you reference a local, a symbol, or anything, if you reference anything and it's a function, it'll call it. If you really want to get the function on its own, you have to put a address of operator for it. You don't do that, it's not the function. So if you take a look at this, function f equals nothing, and ufc is equals s. So this is essentially calling it. So let's just comment out all of that, switch to the tab, and run it. So and the output is main.f takes in nothing. It's a nullary function, so it has an arity of nothing, and it returns empty tuple, and then that. So that's right. So it's just a function. And then main ufcs equals main.f calling. But before it wasn't calling, but now it is calling. Because when you reference a bare symbol, or a bare local, or an L value, and if it's a function, it'll automatically call it. Now, why do you need to do that? So, I'll tell you why. So, I mean, take a look at this. It's f parameter list equals empty tuple. Now, keep in mind that global equals f this is completely wrong. You're not invoking the function with nothing, you're invoking the function with an empty tuple. If you really wanted to make this right, you'd have to do a equals empty tuple. Then and only then are you actually calling it with something. Because this, f empty tuple, you're calling it with one argument. That's not how you call nullary functions. So the issue is, if I don't have this kind of C-like syntax for calling, how do you call a function that takes no arguments? Well, it's simple. You just put it there. You just simply put it there. And that's what I'm taking from UFCS, Unified Function Call, Unified Function Call Syntax. I'm taking this. The idea that if you put a function down, you're calling the function. And it's kind of like how in Haskell, where you can have like main.put sterlen something. And I mean, this isn't a function, it's just it's a global. But when you invoke it, it's essentially like an effect, right? There is no functions in Haskell because everything is a value that produces an effect. So this is how you call functions that take no parameters. Not an empty tuple, they take no parameters. This is a nullary function. So we're not going to this kind of curried nonsense anymore. If you put a function down, it's a function. So that's the one thing that I did. So I explained two things. Actually, you can see... Oh, not clang, because clang's too long. Yeah, I'll bring back the example. You can see how it's just main.f with nothing, and then main.f with something. So you're calling it. The promotion, so to actually call, is here in check expr. So let's go to case expr local. Right. Yeah, so you're getting a local. So it works like this. This is the part in the HIR. It's a node in the HIR, expr local. When you get to here, all locals will already have been resolved. So here, it's just getting a local. Local t, local equals descriptor, locals, expr.d local. So you've got the local. If local.type equals type infer, raise an error. We can't infer the type. So if we did something like this, let a, and then let k equals a, that's uninitialized, but it's also, we don't have a type. All right, then we get to here. expr.type equals local.type. Easy. That's the easiest thing in the world. And then we do this. ufc, so c is the prefix for check, and then ufcs underscore autocall. So promote and recheck if r value, and then you click here. So if the config bm lvalue and config bm call. Now that's a flag that you put into every single call of cexpr. What it is essentially your current context, right? So I can show you where these are defined. So here, it's just a bit flag, bit mask, something, and you call it. So let's say you're calling an expr, like here, global equals expr. So you're going to be calling cexpr with expr and bm r value, because you're extracting an r value. But let's say this was an assignment expression, local.expr. You're going to want to do local with bm l value. Essentially, what it means is, if it's an r value and you're accessing a local, it's going to promote that local to a function call, right? With this kind of thing, yeah. So k equals f, call f. So convert to call and recheck. If type kind expr.type equals type function, construct a call, so expr.call args nothing, and then recheck it. Because I don't want to duplicate logic for calling functions of the unknown size. So I just call I rechecks go cexpr with config bm underscore recall. Now what that actually means is oh yeah, and then and bm call essentially means that I'll explain this. Bm call. So I'm performing f of x right now, and then let's if I want to check x, I'm going to put x in here. I'm going to go actually no. If I want to check f, I'm going to go here, I'm going to go bm call. And what bm call means, don't promote f to a call, right? Because it's already being used in a call expression. Just check it normally. And here, so in here, if config bm l value, if it's on the left-hand side, or config bm call, it's being called, don't promote these. Also, I think these are wrong. To do proper bit. Yeah, if anyone's watching and can tell me, I do not think these are right. I don't think these are. I think they seem right. If I'm using this as Boolean values, I think it's right. I think that's right. I'm gonna leave them as they are. Yeah, so I'm calling bm call, which means don't promote. So don't promote if it's about to be called, and don't promote if it's on the left hand side of an assignment. Pretty simple. And then I do bm recall if I just call bm recall if I'm checking it again, and where bm recall is used is like here. If config bm recall, not bm recall, to check expr again, r value and bm call. So, I mean, that's how we promote them. It's the simplest thing in the world. You just get a local. If it's a function, you apply a call expression, and then you check it again. And that's the simplest thing in the world. All right, what else did I do? Let's find out. Bug fix, move type symbols, recursion, auto call nullary functions, UFCS style, and then feature parity. Okay, that means I'm done. I'm done with checking, type checking, completely finished. So you can compile functions like this. Let's take a look at an interesting function. Like this, factac, factorial with accumulator. Because this one has the type inference in one of the functions. Okay. All right, let's run it. Okay, this is long. This is like, because they all appear on one line. That's the thing. So factac takes an n, which is 932 equals factac n1, and essentially this will reorder it to the front, and then like type check these in different order. That's the reordering pass. Okay, and when it gets to here, factac takes an n ac. It's a recursive function, needs a type annotation, and if n is less than or equal to 1, ac, else, factac, call that with 2 arguments. Run it. Zux zo restore. Hey, welcome to the stream. Okay, let's run it. Good. I mean, simple. So this is the type of fat main factac 0. It's i32, i32, i32. Return i32. And then the type of factac here, we didn't put a return type annotation, but it inferred it. So it's a type i32 to i32. Simple. And I can show you if I remove this, right? It's a self-recursive function, but I mean, how do you type check it? It raises an error. So self-recursive function factact needs return type annotation, and we saw where that error came from. It comes from right here. Self-recursive function needs return type annotation. You're calling the successor with a symbol that's a cycle. Okay. And then we put the type annotation back. Type checks just fine. So simplest thing in the world. It's so simple. Okay. Well, let's get into what we're actually going to do today. Before I do that, let me write something down really quick. Such an old document. Sorry. Okay, alright, let's get into what we are going to do. So first I need to change the title of the stream, because I always forget to do that. Lowering to LIR. Because that's what we're doing today. We're lowering to LIR. So let's find out where LIR came from. So I think you're probably aware. My compiler went from something like this. So my compiler originally went from source to HIR to LIR. So this is my original implementation. And later on, I did source to LIR. That was a big mess. That was probably the thing that I talked about the most. I got it finished. I removed it. I removed going source to LIR, and now I'm like this. Source HIR to LIR, and HIR improved, by the way. This is a much better version compared to the first one. Okay, but now we're done with HIR, let's do LIR. And I'm happy to be finally lowering. So let me explain what the LIR is supposed to do. This is one of the most important things. So, LIR is for proving pattern exhaustiveness through data flow analysis, proving definite assignment through data flow analysis, proving invariance through data flow analysis, performing language-specific optimizations, performing certain global optimizations, inlining, etc., and running code at compile time, so compile time function code execution. So let me go one by one and explain them. Proving pattern exhaustiveness through data flow analysis. So this is what I want to happen in my language. So if v.len equals 2, let a b equals v. Rust can't do this. I wish it did. I mean, I don't know. Does it? I'm not gonna go check. I'm not bothered. But I want something like this to be allowed, and how it's allowed is you need to you need to perform data flow analysis, and if I could do that, it would be great. Okay, now next dot point. Proving definite assignment through data flow analysis. Now, definite assignment goes into this thing called definite assignment analysis. It's this thing where it's like let v. This is what Rust does. If input, so condition, v equals something, else v equals something, right? And then let k equals v. So you're using it. Let use equals v. Okay, this is a well-formed program, and Rust would accept this. But let's say you remove the else case. Now this is a complete error. This is an error because here v was definitely uninitialized. Here v, here v was definitely initialized. So definitely not, definitely initialized. And when you get to here, this is possibly initialized or uninitialized. So you can't use it. You can't use it. The Rust compiler will reject this. But this is something the Rust compiler also rejects. And this won't be input. Let's just say like immutable variable that stays constant. All right. Now this is what I want to allow. This is what I want to allow. V equals 20 and then else v equals 50. This isn't very useful. If you're looking at it, it's not very useful. but this is something where this is a place where it is useful. So let v, if m v equals 20, or use v. Okay, and then more code. Just perform more stuff down here. And then you get here, if m use v. This is rejected by the Rust compiler. This is a pattern that I use all the time in C. I have a variable right here. I don't assign to it, but I use it within these conditional constructs. I use it within these conditional places. I have it in the compiler. I have it in like C code. I use this in C code and all the time, right? So I want to prove that the use of v is okay. I want to prove that v is definitely initialized in places where m is true. And this would be amazing if it was possible. And it's not possible in Rust, because Rust only does data flow like statically, right? It doesn't analyze the like innards of variables that they flow through. So, I mean, I want to be able to use this. This is very important to me, like to get it in the language. Okay, proving invariance through data flow analysis. This is another thing I want in my language. This is something that's, I'll copy an example from down here. Okay. Now, before you read that, let me show you a function in V or something. Let's just create a function in V. I'll copy the bottom. Div p x i32 q 32 i32, and then return x divided by q. And we can go here, assert q is greater than 0. Okay, v or not, this is your average program that you would write. Let's say you have to write a division, like division positive, and you have to assert that q is greater than or equal to 2. Now, this assert takes up space in the code. It's part of the runtime of the function, right? It's going to be present in every invocation of the function. So it's going to be like when you get inside here, you're going to have to call div p with the assert. Let's say div p 25, right? That equals 4. It can't remove the assert. It's going to have to check for it anyway, which is just it's so dumb that like, why can't we hoist this upwards like that? Why can't we hoist it upwards like that? I wish we could, but in most languages, or any languages, I don't even think we can. I don't even think this is possible. I don't think any language has this. Maybe Ada. I'm pretty sure Ada has this, right? I mean, how have we regressed? Like, we moved away from Lisp and stuff like that, and only languages now are getting these features. Okay, so I mean, the whole point of this is, why can't I move this assert outside? Why can't I move it right here? And so now this code doesn't have to deal with the runtime bloat. Now, take a look at this function here. Div p x q equals x divided by q. But I have this thing here called invariant. This is a keyword in the language. It's just called invariant. And it just has an invariant. Q is greater than 0. Alright, and then you just call it, you just call it like that. And this is the function in the language. It's simple, and there's no asserts or anything. This is a specific thing baked into the language. It's called an invariant. So if you did div p, let's say main, right? Calling main, or here, div p 20, 100, 230, and then input, right? And assume input is something unknown to the compiler. The compiler can't determine statically. Okay, now this is a complete error. This will be verified at compile time. It'll raise an error. Invariant q greater than 0 not satisfied. Right? Okay, but what you have to do if you wanted to actually call it, you have to do this. Let k equals input. If k is greater than 0, only then you can do that. The compiler will check that this is only callable inside places where the second argument is greater than 0. So it'll check this invariant for you. It'll raise an error. You can't just call functions. You can't just call functions without checking these invariants beforehand. Yeah, and it's a good thing to have. It's a good thing to have, especially if you're hoisting all these things out, and we can perform this analysis with data flow analysis. That's a thing you can have. So assert will no longer be, you won't, there's no longer, you can't bog down functions by just sticking asserts in them now. Now let's say you wanted to do this kind of unsafely. You could signal to the compiler if k, what's the opposite of greater than? Less than or equal to 0, unreachable. Now this is possible. Let k equals input. If k is less than or equal to 0, unreachable. Now, k is always greater than or equal to 0, and then you can call this. Now, if you compile it with prod, the unreachable will be turned into an unreachable code block. This whole thing will be deleted, and you just sidestepped the compiler type checks. Yeah, so this is just you trade off for some unsafety. But yeah, so this is making code smaller by proving invariance through data flow analysis at compile time. This is something I really wanted in the language, because when I program in C and V and all of these other languages, I stick a bunch of asserts at the top. What if you could put these asserts outside? Okay, and those are invariants. Okay, performing language-specific optimization. So these are things where you know for sure that something is a certain type. Like it's like for some types. But there's also another thing for closures. Let k equal we'll do let c as a constant. So let k k c plus 20. Okay, but what will have to happen is this is a closure object, and the closure data will be a I32 because it has to put c in here. But what you could do is you could perform constant propagation and insert the variable here, delete c, and now it's just a normal function. So this is an example of data flow analysis. You do constant propagation into lambdas, which is something that I want to do. I want to do optimizations to lambdas before we even get into a different to a lower form. Okay, then performing certain global optimizations, inlining. I don't need to explain this, it's just some inlining. And then running code at compile time. I'm probably going to add something like a function. Assume function does something. And then, because I want to have this notion of comp time, but not like Zig's comp time. It'll be like a duck-typed kind of comp time thing. So it'll be like, let a equals const function. So const means evaluate expr at in a comp time context, but comp time is like, it's not like this typed representation. It'll fail. So let's say this function is an input. It'll start constant evaluating and it'll go error, not constant, and then it'll go function. It'll put like line number. Yeah, so this is running code at compile time. So this is what the LIR is for. All right. I plan to go straight from the LIR to C, because C is super simple, and then after LIR I can go to a smaller code representation where I perform more optimizations. Alright, that's enough talking, but I think I explained all of this. So semantically simple like C, simple. No need to compute dominators or traverse graphs. It's nested control flow. Data flow analysis was close to the syntax. Without lowering to SSA. SSA isn't a good target because I'm performing definite assignment. WebAssembly like control structures using indices starting at 0. Okay, that's just an implementation detail. Okay. And I think you've seen this before. lvalue equals expr, ignore equals expr. This is from the original LIR implementation and something that I liked. So if expr, and yeah, so these are all the different kinds of statements, and then ... Yeah, and this is what I talked about before, invariant assertions, like assert a.n equals 2, and then that's possible, because you're inlining it. Yeah, pattern invariance, data flow, blah, blah, blah. Okay, so I'm going to go over what the LIR is essentially like. So if you haven't seen WebAssembly, it's simply just a all the way down structured control flow. In this LIR, and in this language, there is only structured control flow. It's and when I say structured control flow, I mean take from Zig with their block labels. Because you don't need go-tos when you have zigs kind of jumping to blocks and things like that. You can break out of blocks. So let's say you have a function. I think I made an example down here. Just take that. Let v equals k do. Let a mutable a. So let's put that at the front. Loop do a plus equals 20 if a is greater than 0, brk to k with a. Then here, block a. So these are essentially, everything is a block, is a list of statements. Stemmet is assign, etc. Control, flow, things like that. And then, like, a block just contains, yeah, so this is the top level. This is it contains 2 statements as a block. And this block contains more statements. Loop is a statement itself containing inline. And then statement. This is a statement. This is another statement and statement. This is the last statement. So this isn't your normal compiler IR. It's not it doesn't use control flow graphs. It doesn't use any of this weird like phi stuff. It's just simple imperative control flow, like you'd find in your normal imperative programming language. There's no need for these go-tos and things like that. It represents the syntax closely, and there's a couple of reasons why. One, it's super easy to lower to C, and 2, right here, no need to compute dominators and traverse graphs. Everything stays right next to each other. Sudo Nick says, what does FPLC stand for? It stands for Functional Programming Language Compiler. It's my programming language I'm working on. I have a YouTube channel and I post VODs there. And right now I'm implementing the LIR. So I've implemented the HIR, which is a tree IR. It's like the AST, and I'm going into the LIR, which is the lowered IR. It's statement by statement. It's a smaller representation where I can do language-specific optimizations on. Okay, so essentially, just if you've seen WebAssembly, think WebAssembly. It's exactly like WebAssembly, top to bottom statements. Semantically simple like C, list of statements. So let's just go implement it. Yeah, sorry about that. So I'm going to be reusing a lot of the code from the first LIR. As you can see, it's pretty simple. I think I put an example here. Here it is, the LIR. So this is the current LIR, well not current, this is the previous structure of the IR. So this is the struct LIR statement. So all statements in LIR assignments. L equals F, so L value assignment. Empty equals F, user explicit discard, and just F, compiler ignore a value. Since all the compiler ignore stuff has already been solved, because we just type checked over in HIR, we can just remove this. So now we're left with 2 statements, 2 assignments. So this one's an L value, and the next one is compiler ignore. Okay. This is simple. So we can take this. So this is in the current lir.h. So let's move this up. Let's Control C, lir copy, and just move that to the top. lir.h. Good. Now let's create the LIR. So let's just delete all of this, all of the old stuff. It's all gone. Yeah, so every statement, let's just create, let's say like A equals 50 plus 24. It'll eventually end up like this. A equals 50 plus 24. There is no intermediate values in LIR. Everything is so it's like everything is on the left hand side. everything on the left-hand side is essentially packed into an L value, and that's right here. LIR L value, it's a local or a symbol in a list of projections. DREF field and index. And everything on the right-hand side is a tree. So we're still keeping the tree representation. So it's like we're mixing this imperative WebAssembly or C-like control flow with everything on the right-hand side being a tree. So we can easily translate it back to C. The thing is, all of these things here, invariance, definite assignment, or everything here, right? We're not performing global code motion, global value numbering. We're not performing any of these super complex optimizations. What we need in LIR is these things. These three top lines: proving, proving, and proving. This is an IR for proving shit. So we don't really need all these complex things to store. Like, we don't need SSA. SSA would only hinder us. So that's where I'm going. This is what I'm going for. All right, so let's just start creating it. I'm gonna delete everything in here. Bring this all the way up to the top. Delete it all. And I'll put lir.h on the side. So let's just take the L value, because this is what we're keeping. Proj IDX invalid, keeping that. L value and L value. Good. All right, and then the LIR value is basically this tree representation. Yeah, it's basically a tree. I wonder if we can use HIR nodes on the side. No, probably not. No. But, yeah, okay, so struct LIR statement. Let's just create a statement. Let's copy the type def from the top. Yeah, I hate type defing. So, all statements in LIR. So, L value assignment and ignore. All right, and then we have the rest is control flow. So, statement L value, statement discard. Yeah, statement discard. All right, and then there's going to be control flow stuff. So let's just do if. I think. Should I do if or? I was thinking if I should represent everything as a case statement. I don't know. How does the new IR make it easy to prove things? Multiple ways. So after you're done type checking the HIR, it's essentially a big tree, right? So you have all this tree stuff. But the big error is control flow, right? So let's say you have A equals if C dot 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 else dot dot dot, and then you perform more control flow, and then there's also loops, right? There's also a loop keyword expr, and that performs more control flow. Basically, if you're going over an AST, it is impossible. It's not impossible, but it's really hard. And you're going to be tripping over your own feet. You're going to be doing all these things. It's going to make your life hard. But let's say you're in LIR, or if you're in a control flow graph. LIR or control flow graph, they basically make these things really easy to perform data flows. So let's say, so if it's this moving things into statements instead of expressions. So an assignment in the HIR is let's say equals this. An assignment is an expression. This expression here, it's an expression, but I really don't want it to be. And here, this if is an expression. I don't want it to be. So I put down these rules. So every statement, let's say if I'm turning this thing, it'll essentially be like this: a equals 20, and then expr equals a. So I'm essentially flattening these things, and then this thing, a equals if. It'll be like if C, and then another code block, then code block. So essentially, I'm not performing any control flow graphs, But what this does is it turns my expression-based value code, right, in the tree, because this is a functional programming language, into an imperative style if cases. And this makes things really easy, because when you get to here, I'll explain the difference. I'll explain why this is a lot easier over control flow graphs, especially for what we're doing. Let's say you have case 0, case, all of these things. Let's just do 3 cases. And then jump to exit. And exit is like v I32. Use v. And let's just say this is a fine node. These are essentially fine nodes. Go to exit 1, 2, 3. Right, and when you get to here. So, think of control flow graphs as as the control flow inverted on itself. So what I'd have to do if I wanted to perform conditional constant propagation and these kinds of definite assignments, I need to start here and then gather all the dominators, like successors. So I need to go start here and then grab case 0, case 1, and case 2. But what would be easier is if I could just have switch and then just like have all these cases, case 0, case 1, case 2, right, packed in already, and then that's still in the block of exit. So just think of it like I'm turning my expression-based language into C, and not a control flow graph for specific reasons. And this statement by statement thing makes things easier to do data flow analysis. Yeah, it's, trust me, it's a lot easier over an AST. With an AST, it's utterly hopeless. You have a lot of trouble. This is needed. This is absolutely needed. Yeah. Okay. Okay, so let's just let's add a control thing. So what we really need is statement. We'll need a way to break out. So statement if. Yeah, we'll do this later. We'll do this later because we need to figure them out properly. So statement L value. L value is des. Let's just do D L value. And then union. Yeah, okay, D value. Yep, and that contains a LIR value T. Now these. So this dest equals D value. Dest equals D value. Okay, simple. This is a simple statement. 2 different states. Union for a dest, union for a value. We're going to add more things, so we're going to put more stuff in the union, but this is good for now. Good for now. Okay, well, let's create a, I don't know, a block? All a block is a list of statements, so we'll leave that to last, but let's just take a look at... Yes, this is the LIR term T. This is when I was doing a control flow graph, and I had explicit terminators. Alright, but what we have now is just the LIR underscore value T. This is just LIR value. This will be our, essentially our tree. So we're going to have to lower it. Alright, now let's bring this value up. Oh, shit. Alright, let's go down. Value integer literal, value bool literal, value array, value tuple unit, value tuple, add, sub, mul, div, mod, eq, not equal, less than equal, less than, greater than equal. greater than and or negate not. Address of slice. So we don't need these things. Yeah. I think. Yeah. Value slice on L values. Cool. Cast size of L value. Okay. No, we don't need these. Good. Good. It's control temp. Yes, this is a super simple trimmed down AST tree thing. Yeah, it's super simple and trimmed down. I think that's it. We can reuse a lot of this code. I think I'm gonna write a note down here. Yeah, late docs syntax. All right. Okay, this is a note to self. Oh, here's the LIR. So, let's start lowering. Easiest thing in the world because we already have basically all the code to lower. So let's just start. So let's create. What should I name the file? Lowering? Lower. Lower. Lower seems fine. Okay, and this is the main function check. So when you call compiler check, it creates a rsim PO. C, yeah, so this is reordering, creates a list of symbols to check in that order, and then check all symbols. So I want to, I might want to rename this function compiler check. Compiler passes. Yeah, I don't have a proper name for these things. Okay, C, L lower, all symbols. Okay. So, lower.h. I think I want to rename this function as well because this is like the main entry point. Sudo rename. Okay. All right, lower.h. I want to copy the this thing lower.h. So, I'll lower all symbols. Fragment once. Fragment once this as well. Good. All right, let's call in. We'll get a linker error. Must use struct tag to refer to type LIR value t. Where? Oh, I don't have that. All right, good. So let's start include .h, and then we'll go to check. It shouldn't really name that, but it's okay. Good. Okay, let's get a linker error. Good. So we're going to go symbol by symbol. just like this. So just steal, just take it all, paste it. Good, cproc c global. So yeah, there's no need to check for these. Void L proc, lower proc. Don't know what the thing is. That's just this proc t. All right, L proc, void L global. Spider. Oh hey. First time catching you live. I'm watching a few videos. You mentioned them, so it was really cool. Thank you. Likewise to you. Okay, so let's get to lowering. Global and procs. We're just gonna be calling these things. Global. Insert not reached because we haven't done that yet. Right, let's get an assertion failure. Let's do f equals f to nothing. That's what we're gonna do. All right, now unreachable. So let's start lowering. So I'll show you where this is the representation of a proc. A proc contains an IR desc T, and why it's called that is because the HIR and LIR. HIR is the tree IR. LIR is the list of statements going one by one, right? Do our optimizations on and analysis. So the LIR and HIR actually are supposed to be really similar. They're coupled right next to each other, and that's why they just share. They share the globals. They share the list of locals, and locals is just all this stuff. That's why they're right next to each other. So let's go here and uncomment that. So we have an LIR proc t, and we'll see why that's erroring. Because we don't have an LIR proc t, so let's go make one. So an LIR proc t is just a list of blocks, but in our case, it's a list of statements. Statements, great. Oh, we also need a statement return. Yeah. Return the value. Okay. To okay. Type definite. Alright, where's this error coming from? Surprised. Is this not what's Clang? It's Clang D. Okay, it was Clang. Alright, where's the assert failing? It's failing in lproc. Okay, we can go start. Let's go start right now. Okay, check expr. Yeah, so all we have to do is iterate over the HIR and generate a LIR. How did I do that? Actually, it's I have to take inspiration from the first LIR compiler, essentially. This is a single pass compiler that generated what did it generate? It generated a control flow graph. So it's pretty sophisticated. And I'll show you. Essentially, it has an LIR block T and it depends. So if you are compiling something like this, A equals A plus 20, or A equals A yeah, it'd recurse into here and it would reach this A equals 20. So it'd go to A equals 20, and then it would return a L value of A, and then it'll recurse back down, and then it'll see expr equals A, and then do that. So essentially, all assignments don't return a value; they are hoisted into statements. Pseudonic. Eventually, would this compiler transfer the code to C x86 LLVM? So LLVM is no go. I'm not doing that. So they're gonna go to essentially what I want is WebAssembly code generation. I want RISC-V code generation, 32-bit and 64-bit, possibly x86, and what is absolutely needed is C code generation. The reason why I'm choosing C as my target for code generation is because when I want to bootstrap my compiler on someone else's machine, I want it to work first try. C is the most portable thing in the world, and there's a reason why V uses it to use it as a code generation target. They overdo it sometimes, but it's good. It's a good principle to generate C code. The Glasgow Haskell compiler does it. That generates C code for porting to other architectures. The first code generation thing I want to get up and running is C, because it's the easiest and works great, portable. Yeah, so I'd like have an entry block, I'd create a new block and things like that. So yeah, I'm gonna have to kind of less talking and more writing. I won't be able to explain much to you guys. So you'd obviously have a void L. Sorry, it's a tree. It's a tree, so it'd have to return an LIR value T. Which C compiler would you use on top? Since C compiler is secondary, you won't really be using C. C is left up for people using it in build scripts and people using it for specific things. It'll just generate a C file on disk or to standard out. It's completely at the choice of the user. I'm not going to add any kind of searching for C files or anything. It'll just generate a big blob. So no need to do anything special there. All right, so okay, we need LHIR expr lower HIR expr. So it takes in a IR desk T desk and a stem T pointer statements, because this is a list of statements, and a HIR T pointer to expr. Good. Now what we do is essentially we're gonna have to create. Let's create functions for generating this HIR. So let's just go like we'll have to do void LIR statement. So it contains a not an IR desk, that's not needed, but it's just a pointer of the statements and a statement, and then you have to do a LIR dup. LIR dup is just for allocating on the heap, so it just takes a value, turn the pointer to that. What else do I need? Not much, really. Alright, so essentially for a proc, we have to do this. And then first convert to indentation of tabs. So we call LHIR expr on proc desk. Desk HIR. Okay, we need to create list of statements. So LIR statement T statements equals null. Statements. And the address of proc desk, and then we'll just return a value. LIR value T value. Right, and then we'll do LIR statements. Nope. Address of statements value. Taking a pointer? I don't want to take a pointer. Oh, we're going to create a statement. Why is that an error? Return dest value. Why is that incomplete type? I mean, not dest, it's a d value. Great. It's pretty simple. Simplest IR compiler I've ever done. It's not this kind of control flow graph. So let's just do a switch case over the whole thing. Switch. Yeah, it's gonna be the easiest IR I've ever done. Probably the most versatile as well. So it's gonna go straight to C. Alright. So let's just go over list of kinds. Whole thing. Yeah. Paste. Indent, undo, all the way up. Right, case. Good. And then default. So, first thing. That is the simplest thing. You just do a value. It's your literal, because it's the same thing. Yeah. The more I write, the more Copilot will become accustomed to the like what I write. Great, I get Copilot for free because I do open source with the VM and the V organization. They just give it to me, which is great. So it's something I can live without, but it's pretty good. Okay, so we don't need type here. Pseudonic. I had a similar idea inspired from sorting. Scripting language compiler. Use binary. Can we run on all OS and Arch using Cosmopolitan compiler? Yeah, that's pretty good. Source code of any project. Using it would include the binary too, and anyone can just run it with the project with any external dependency. Yeah, that's pretty cool. That's pretty cool. You're like cutting the middleman out if anyone was to like install like a scripting language like Python or something. Yeah, not bad. You know, there's a language that I looked at a while ago. I think it's called like it compiles to shell script. Kotowali. VLang, GitHub. All I know is that it's written in V. Kotowali language. This one. A statically typed scripting language that can transpile into POSIX shell script. And it's like kind of like V syntax, but it's got this kind of like piping and things like that. Anyway, the whole point of this is that it compiles straight down to shell script, right? I mean, the most annoying language in the world is shell script, right? Going straight line commands for shell script is okay, right? It's fine. But if you want to do anything remotely useful, it gets out of hand quickly. This is a kind of language like that. I mean, because there's only two things constant when you go on a new Linux machine, right? You get a C compiler, and that's kind of not really often these days. Sometimes they don't even have it installed, pre-installed. You get a C compiler and you get a shell script, right? So you have two things to work on that are constant in all machines. So I mean, I wish I wish they made it a standard so that you could run something like WebAssembly as as like shell. If shell could support WebAssembly, that'd be great. Because then you'd have a WebAssembly interpreter on every single POSIX machine. That's just kind of thing I'm interested in. I mean, imagine if shell script had their own kind of, I don't know, like this and like shell scripting thing. I don't know. I don't know. Yeah, just there's only two constants on Linux machine: a C compiler and shell script. There's the only things that are portable. Your idea is really good though. Using the Cosmopolitan thing. Yeah, that'll work on all machines. Alright, so it's an LIR value, T kind is a value integer literal. So all it is just D integer literal equals D integer lit. Okay, now the types of expressions Are we gonna store the type? I don't know. I don't know if we need to store the type, because what if we're doing something like a plus b, all the types are explicit anyway. I don't know if we want to go typeless. What we definitely want to do is we want to go types in integer underscore lit. We'd want to go type to there. That's the that's one of the annoying parts. Like, where do I insert the types? Because I don't really want to insert types yet. Okay, so let me remove all of these value numbering. Yeah, we're not doing GVN or LVN for that matter. To do, where you put where do you put the types? Because I really know the types. So we'll do the types later. We'll just ignore the types for now. All right, bool literal. Yep, complete array. One return. Great. No. Yeah, expr.d array. Yeah, this is just a simple conversion. I feel like we could convert the HIR into a flattened representation like Gimple. I don't know. This is just me thinking. And compatible pointer types. Okay, so this is where we need to do. Okay, this is where we can't do anything special like that. So let's just go LIR value t values value pointer equals null. 4 equal to I equals, yeah, good, and remove that indirection. I'll push. Great. Okay, well that makes sense. Case expert tuple unit. You know what to do. Great. No lambdas. No matches. Now this is where we have control flow. So not yet. Not yet. Not yet. Case expert is signed. So we need to create a statement. So how did I do it before? How did I do it before? Because there's a way. You assign. LIR inst L value. Okay. So the assignment has LHS equals RHS. So we need to construct a L value. Well, okay, we'll leave that for later in a bit. Okay, we'll do it now. So this is where I explain L values. And L values is something I take from Rust's MIR. It represents the entire path traversal, derefs, indices, indexing to other locals and things like that, all in a single unit. So let's say you have something like this. A.field 0 equals something. Okay, so essentially it is a L value equals 50. And what that L value is, it's A, and then L value of fields, an L value of index 0. Just like this. Field. So this whole thing is an L value in itself equals 50. So if you look at the structure right here, it's just LIR L value. So it's a union between a local and a symbol. So just because you can assign to globals. And here, LIR L value projection T. So it stores the local here. Yeah, so A dot field index equals 50. So this compiles into the starting thing. This is the local. This is the very start. And then a list. And what this list contains is here, LIR value projection. Oh yeah, this is an old. Yeah, fucking Clang indexing. Okay, LIR value projection. So it's an enum deref field index, and it just contains these things. So it's basically a list, fields, index, and that sort of thing. It's pretty easy to understand. It's just you have a local and an array of projections all the way, and it makes these things really easy to understand. All right, and then just delete these because I won't be doing them yet. So what we need to do is convert a HIR L value into a L value. So we're going to do LIR L value T. L HIR L value. Takes in a IR det. It doesn't need to take in an IR det, but it needs to take in statements, because evaluation of an L value could produce intermediate values, and a expr. So switch expr. It would need to recurse. It would need to recurse inwards. L value impl. And this takes an L value. Yeah, that seems about right. Well, I need to find it. I need to remember how the tree is represented. Yeah, you need to recurse all the way down to the bottom, which is just annoying. Okay, alright, so let's just produce an L value. L value equals empty, and then you just call this LHR L value impl. Great. And then return L value. Wish I could take the address of the return value pointer and remove this intermediate value, but that's just something we can't do yet, or even express in C. It'd be great to express it in my language. I think Zig's talking about it. Okay, switch case, just a big switch case. Expr.kinds. And what are all the L values that can be kept? Now, what we do check, the default case would be assert not reached, because we've already checked this. The type checker is doing its job to make sure that all L values are in the right place. I can show you where that's done. It's being done down here. Let's just go to expr assign. Okay, calling C assign. So essentially how you type check an assign is you have the left-hand side and the right-hand side. You type check the left-hand side and you type check the right-hand side and ensure that the left-hand side is a L value and that it's mutable. So we'll go in here. So it has expr local and expr deref. There's only two things that we have right now. Should probably do field accesses. Sudo access, since we already support them. We already support field accesses, so why not these ones? So local and deref. Okay, we'll just do local today. Case export local. Great. We'll do L value dot local equals expr dot dlocal. And we'll do is lock. Yeah, because we're kind of doing this in the inverse order. Yeah, because this is you have the local and then projections, projections, projections. But with the tree, you'd have the local at the very top, and you'd have a field access, field access, field access, and this is the root. So you'd have to go backwards with this sort of AST thing. You could do it with a sort of forward recurse. How could I even do that? I don't know. I don't think you can. Okay, but this is good. L value, sim lock projection local symbol, done. Break. And then just return. Right? Return. Okay, you're not returning an L value here, but yeah, you just done. Good. I mean, that's it. So in X per assign, we just do this. See X per L value statements. No ref. Deassign LHS, and then you'd want to do LHR expr. Okay, let's get. Right, now let's construct a statement. Oh, yeah, it just had the right thing. Well, kind of like the right thing. Estimate L value. Okay, well, I'll just call it assign. Prefer it like that. Yeah, that's much nicer. Alright, and then, yeah. Dest. Right. Well, dest is L value. D value is RHS. Right, the med name is just LHS. Simple. That's simplest thing in the world. But also, assign is an expression, so we need to reload the value. So let's just return not RHS, but we need to return a reloading of the variable. So let's just reload it. LHR UT kind. Oops. Do we have a value local? No, we need to construct an L value. Here, we have value L value. We need to create as lock as well. Lock equals expr.lock. Yeah, don't forget the locations. We'll do the types later. Like we're gonna immediately lower the C as is. Like I think that'll make for a fun stream. Next stream we can lower the C. All right. Tom. Because I mean this is pretty easy. The DL value is LHS and dest. Do we even have dest? No, there is no dest. So yeah, so value L value and the L value is just a LIR L value T, and the local is local. Yep, that's right. And then lock is just the same. Proj symbol. Nope, easy. Done. We're reloading the local. Infix, postfix, prefix. We can just do that. Call it again. LHS, RHS. Yep, great. Okay. So now we have explicit add sub mul div mod eq neek. So we have to do switch case. Let's do a associative array sort of thing. So which things are infix? These are all infix right here. So how did I do it? I think I already have one of these things. Yep. Talk to op. These are one of them. Okay, we'll just take this. Talk to op. And then we can just remove the inst out the front. Yep. I have isn't is one of them. Alright, talk to op. Make sure you mark these thingies as static const. Const isn't enough. I've seen in a program where they had this kind of associative array or array construct for UTF-8, right? And you'd put in the byte and you'd go to certain positions and return a number. I think it was in the some AI thing. Essentially, this wasn't marked static const, it was just marked const. And what happens is you'd have to construct this on the stack. And the thing is with these associative arrays things, they get pretty big. So, and this doesn't change. I just rather this be in static memory. If it's non-static memory, it'd cost like 10 instructions to create. So mark the static const, always. So, great. Yeah, so the kind will have to be this, top to up. The infix dot kind. Yep, and then lock, and then dinfix, they share LHS and RHS. So after this, do LIR dup, allocate on the heap. Great, that's done, that's easy. Postfix and prefix, we can ignore those for the moment. We could ignore all of these. We can do these all later. At this point, I just want code gen. Value L value, that's great. Symbol. Nope, value L value, and then the L value. Nope, symbol. The sim. Bro. Okay, casting, we can ignore calling. All we have to do is just do that. Coolie. You like the word F. And args. So yep. With args, LIR value T value call, and dump F. Great. Break, continue, return. Return, we just need to create a statement. So that's easy. I feel like this oh yeah, to do. I need it. Yeah, don't worry about this for now. Yeah, I feel like this IR is just too easy. I don't know, because I'm just so used to working with control flow graphs and everything. The hard part is the analysis. Alright, expr voiding. Well, we can just do this, because it's a simple one. Void, how it works is void expr. It always evaluates to empty tuple and discards essentially the expression. This is for like effects, things like that. So value void, it's not voiding it. All it is this new statement. LHIR L value LIR statement. And we're just creating a ignore. STMT ignore. Or is it? I don't know what it is. Is it STMT discard? So we're just discarding. Return. Value. Tuple unit. Well, okay, that's not right here. Create a statement. LIR STMT. Well, now we have to return something. Huh. We'd need to okay, this is an issue. Since the return in my language is actually an expression, so you can have let a equals ret 20. And the value of this is no return because you've essentially left the function. But what I want, I should probably run a pass beforehand that removes all this dead code, because I can't really handle this expr return stuff. Because what value do you return? I don't want to return a no return, right? I think I'm just going to return a empty, like, I don't know. I don't know. I feel like I should run a pass on the HIR beforehand. Yeah. So I'm gonna remove this for now. To do. What do we return? I don't know. Okay, field and let. You know what? I don't need these. So great. We essentially did basically all we need. So let's just run it. See what happens. Alright, so we have linker errors. LHIR expo and LIR dub. So let's just get this done real quick. You have an LIR.h? LIR.c. Now we go up to the top. Well, what we need to do is pretty simple. It's just these things. It's just easy. Just allocate on the heap. Thank you. And just our push statement. That is so simple. They could be inline functions. Great. Let's go back to lower. So, lproc. And that seems it. Let's just print out. Done. Done. Do we even get here? We do get here. All right. Well, let's just start printing the LIR. Let's just start printing the LIR. So how we can do that is in table. Table is where we do all the debug printing, because it's where we iterate all over all the symbols. So let's just start by printing them all. Then after I'm done, we can end that stream. We can end the stream and see what to do next. So dump function. Now what I want to happen is if we don't have the LIR or the HIR, print nothing. If we don't have the LIR, print the HIR. Yeah, because it's printing the HIR. Okay. Printf. So, if sim dot dproc dot desk dot, we'll go to desk immediately. Desk. So if we even have the LIR, we print the LIR. If not, print the HIR. Print HIR equals. All right, and here we just do printf LIR and no equals. Do a new line. We'll increment tabs plus plus. Then we'll go print estimates. All right, let's go over them one by one then. So we have a function. Print exper. Print estimates. LIR estimate t. What is that print statements called? Statements. Print statement. That's how I just like to do it. And then 4. Right. Do print tabs. No one. All right, now we do a big switch. Yeah, assign, discard, return. Printf, and we have facilities for printing an L value. Print L value. Do we have L values? Oh no, we don't. So we need to create that. But what we do is we have old code for printing. Do we? So L value print. LIR. There's the L value print L value. And just steal all of this. Let's see, is there any errors? Remove this. Oh, we're taking a proc T in a desk, right? Yeah. Desk. Alright, good. We'll print left-hand side. Estimate.dest. Do nothing. Return is ret. Static void print value. No filling. Is it D value? Alright, now we can do the fucking big switch case. That's the old one. We just do the ones we implemented. Actually, no. We'll delete a couple. Lambda do block if. Yep. Good. We'll do a switch. Value dot kinds. Then we'll just get a release inside. Oh, these are oh fuck, these are experts. I copied the wrong thing. Okay, that's my fault. You know what we can do? We can just steal. We've already printed this. Oh, so annoying. Yeah, done. Just take the whole thing. Wow, same name as well. Just print value. Yeah, that's a good thing about having this. This is old. Desk T. We name this the desk. Yeah, it's not like much has changed at all. Alright, well, let's do it. Too few arguments. Well, it type checked. I don't know why it didn't call it. Yeah, why is it not printing? If desk.lir statements does not equal null. Where's the lowering come from? Oh, I'm not setting the statement. Oh, fuck, it's so dumb. I'm not setting the statements. I'm creating them. Okay, fine. Proc desk. LIR? LIR, yeah. It's like that, right? Oh, LIR proc T. Statements. Right. That's right. Okay, let's see. Does it work? Good. Main.f goes into LIR, ret empty tuple. Okay, let's see what we can do with something more complex. Right, so we don't have var decals, but what we do have is we don't have if statements, but let's just do it anyway. Oh yeah, there's no that anymore. Now I can bank on the fact that it'll compile it it'll compile at least one of the functions, and then we can see what happens. Unreachable. Set unreachable. Okay, you know what we can do? We can just do rewinds. Error unwind. We'll do error unwind instead. To make it do set jump. Okay, so it raised an error and couldn't do all of them, right? It's still HIR. Wonder what the error was. Wonder what statement we didn't get. Pretty cool, right? Yeah, we'll do a different function. X, Y. X plus Y. Alright, what does that do? Does that work? Okay, main.add ret x plus y. Okay, good. We'll add a bit, we'll make it a bit more complex by adding an assignment. Y equals 5. Okay, so now it hoisted that expression into a statement. So now we get y equals 5, ret x plus y. Good. We can do that as many times as we want. Oh, this expression isn't a null value. I don't know. It seems this should be right. Let me jot that down in syntax. This should be possible. I think I have an issue with my expression parser. Issue. Yeah, these notes are amazing. Okay. Yeah. Anyway, this is good. This is good so far. And we'll do like x add 20. Let's do this one. Right, ret main.add called with x and 20. So this LIR so far is like a move down implementation of like HIR, where all the expressions are moved into statements. I think that's all I'm gonna do this stream. I think that's it. I'm definitely gonna do more off stream, but the important parts are gonna show on stream. I think that's where I end off. I added a lot of files. Let's add them all. What stream is this? 15? Wow, it's stream 15. So I did check. What did I change in here? Nothing. So just lower plus LIR. Lower to LIR. Done. Alright, if anyone has anything to say, say now, but I think we're gonna end the stream. Let me commit. I'm considering, I don't know, I'll have to implement I'll have to implement a simplification pass of the HIR. A simplification pass that removes dead code, that makes it really easy to implement the returns and stuff like that. But I think I'm done. Yeah, I'm gonna end the stream. Thanks, Nick. All right. So, I do this HIR, I do this LIR lowering. Once I'm done with that, C code generation is the easiest thing in the world. I'm basically done. I've came here for what I accomplished, and then I can do more things later on, but getting C code generation is the most important thing. And this language didn't take that long to implement. Spider. Bye. Thanks. Yeah. Thanks guys for showing up. But it's the end. Good night, because it's late for me. It's 2 a.m. So, yeah, good night.